Frank Whittle stood in the cramped quarters of RAF Cranwell in 1928. A skinny 21-year-old flight cadet with grease under his fingernails and equations scattered across his desk. While other cadets focused on mastering the biplane trainers parked outside, Whittle filled notebooks with sketches that looked nothing like any aircraft engine in existence. He drew turbines, compressors, combustion chambers arranged in ways that made his instructors shake their heads. The problem consuming him was simple. Propeller-driven aircraft had hit a wall, literally. As planes approached 400 miles per hour, their propellers lost efficiency, chewing through air that became too thin at high altitudes and too resistant at high speeds. Whittle saw the limitation clearly. Propellers were trying to push aircraft through an invisible barrier they could never overcome. His solution emerged during late-night study sessions. Forget the propeller entirely. Suck air into a compressor, squeeze it, ignite fuel in the compressed air, and blast the expanding gases out the back. The jet of exhaust would shove the aircraft forward through pure reaction force, the same principle that made rockets work. No propeller, no complexity, just air, fuel, fire, and physics. When Whittle presented his thesis, Future Developments in Aircraft Design, to his superiors in 1928, the response was ice-cold dismissal. His instructors called it impractical. The Air Ministry's chief scientist declared that jet propulsion might work, theoretically, but would require such massive fuel consumption that no aircraft could carry enough to fly anywhere useful. Senior officers reminded Whittle that real engineering meant improving existing technology, not chasing fantasies. But Whittle couldn't let it go. While stationed at various RAF bases over the next 2 years, he refined the calculations during every spare moment. He worked out the thermodynamics on scraps of paper during night watches. He sketched compressor blade angles in the margins of maintenance logs. The mathematics kept proving him right. A jet engine could work, could deliver thrust at high altitudes where piston engines gasped for air, could push aircraft past 500 miles per hour. By 1930, Whittle had transformed his thesis into detailed technical drawings. His design showed a centrifugal compressor spinning at extraordinary speeds, 18,000 revolutions per minute, sucking air inward and flinging it outward into a ring of combustion chambers. Fuel would spray into those chambers and ignite. The hot gases would blast through a turbine that powered the compressor, then exit as thrust. Every component was calculated, specified, drawn to scale. He took the design to private engineering firms. They looked at the drawings, nodded politely, and showed him the door. No one would risk capital on an unproven concept from a junior RAF officer. The Air Ministry, asked again to fund development, responded with bureaucratic silence. Whittle was 23 years old, technically brilliant, and completely alone. On January 16, 1930, Whittle filed British Patent 3/14/6 for a turbojet engine. The patent office accepted it. The engineering establishment ignored it. And Whittle, unable to afford the £5 annual renewal fee on his meager RAF salary, would eventually let the patent lapse. His revolutionary design entered the public domain, free for anyone to use. For the next 6 years, the blueprint for jet propulsion gathered dust while Whittle flew training missions and watched Europe slide toward war. The patent cost £5 per year to maintain. Whittle earned less than £3 per week as a flying officer. In 1935, after paying the renewal fees for 5 years while watching every major aircraft manufacturer ignore his design, he made the calculation that crushed him. He couldn't afford to keep protecting an invention nobody wanted. British Patent 347/206 expired. The turbojet engine design, complete with detailed drawings of the centrifugal compressor, combustion chamber arrangement, and turbine assembly, became public property. Anyone in the world could now build Whittle's engine without paying him a penny or asking his permission. The Air Ministry didn't notice. The aircraft industry didn't care. Whittle felt the particular sting of having created something valuable that the world had declared worthless. But something shifted in 1935. Hitler's Germany was rearming. The RAF began expanding desperately, and a few former RAF officers who'd left for private industry started reading old technical papers with fresh eyes. Two of them, Rolf Dudley Williams and James Tinling, stumbled across Whittle's expired patent while researching high-speed flight. They found Whittle teaching at the RAF's Officer School of Engineering, still sketching turbine improvements in his spare time, still believing his engine could work despite 5 years of rejection. Dudley Williams asked the question no one else had. Can you actually build this thing? Whittle pulled out updated calculations. The numbers still worked. Better, actually. He'd refined the combustion chamber design, improved the compressor efficiency, solved cooling problems that had haunted the original patent. He needed money, machine tools, and a workshop. Dudley Williams started knocking on doors. Finding investors in 1936, Britain meant convincing bankers that a junior RAF officer had outsmarted every established aircraft engine manufacturer in the country. It meant explaining thermodynamics to men who understood balance sheets. It meant projecting confidence about an engine that existed only on paper, while the Air Ministry's official position remained skeptical silence. Dudley Williams and Tinling scraped together initial funding from a small group of investors who saw war coming and understood that air superiority would decide it. On March 27, 1936, they incorporated Powerjet's Lomond, with Whittle as chief engineer. Total capital, $2,000. For comparison, Bristol Engine Company's annual budget exceeded $500,000. The Air Ministry finally took notice, barely. They granted Whittle permission to work on the engine project part-time while maintaining his RAF duties. No funding, no facilities, just permission not to be court-martialed for pursuing private engineering work. Whittle taught classes during the day and designed turbines at night. Powerjets rented a small workshop in Rugby and hired a handful of machinists. They contracted British Thomson Houston to manufacture components from Whittle's drawings. Every part had to be fabricated custom. No supplier made combustion chambers designed to withstand 1,100-degree flames. No manufacturer produced compressor wheels meant to spin at 18,000 RPM while handling massive airflow. The work consumed 2 years. Whittle spent 1936 and early 1937 translating his calculations into metal, confronting the gap between theoretical designs and actual engineering. Bearings failed. Welds cracked. The centrifugal compressor, which looked elegant on paper, fought every attempt at precision manufacturing. Each component arrived late and over budget. By April 1937, Powerjets had burned through most of its capital building a single experimental engine. The investors were getting nervous. The Air Ministry remained uninterested. And Whittle had an untested prototype sitting in a workshop representing either the future of aviation or the most expensive failure of his life. He decided to start the engine and find out which. April the 12th, 1937. The experimental engine sat bolted to a concrete test stand in the British Thomson Houston factory in Rugby. Whittle had designed every component of this machine, but he'd never seen them all work together. No one had. Jet engines didn't exist yet. The prototype looked strange. A bulbous metal casing about 4 feet across, bristling with fuel lines and instrumentation cables. Inside, a centrifugal compressor waited to spin faster than any aircraft component ever built. 10 combustion chambers ringed the compressor, ready to maintain continuous burning at temperatures that would melt ordinary steel. Behind them, a turbine would extract just enough energy from the exhaust to power the compressor while letting the rest blast out as thrust. Theory said it would work. Metal had other ideas. Whittle stood behind a reinforced concrete barrier as technicians primed the fuel system. The startup procedure was untested. They would use an electric motor to spin the compressor up to 2,000 RPM, then introduce fuel and hope the combustion stabilized before something catastrophic happened. Safety protocols were primitive because no one knew what could go wrong. The electric motor whined. The compressor began spinning. At 2,000 RPM, fuel sprayed into the combustion chambers and ignited with a roar that rattled the factory walls. The engine accelerated. 3,000 RPM. 4,000 Rs. The noise climbed to a shriek that made conversation impossible. Whittle watched the gauges climbing. 5,000, 6,000, 7,000 RPM. Then the fuel pump governor failed. Fuel flow went uncontrolled. The engine accelerated wildly. 8,000, 10,000, 12,000 RPM. The test stand shook. The shriek became a scream. Whittle shouted to cut the fuel, but the controls weren't responding. The centrifugal compressor was spinning faster than it was designed to handle, and the forces trying to tear it apart were mounting exponentially with every revolution. At 13,000 RPM, someone finally killed the fuel supply. The combustion died, but the compressor kept spinning, coasting on its own momentum, winding down with agonizing slowness, while everyone waited to see if it would disintegrate and spray turbine blades through the factory like shrapnel. It held together. Barely. When the engine finally stopped, Whittle walked to the test stand on shaking legs. The prototype was intact, but had operated thousands of RPM beyond its design limits. They'd proven the engine could run, could generate thrust, could maintain stable combustion. They'd also proven it was trying very hard to destroy itself. The second test run happened days later, after installing better fuel controls. This time the engine behaved. It spun up smoothly to 8,000 RPM and held steady. The combustion chambers maintained stable flames. Compressed air blasted out the exhaust as a focused jet. Whittle's calculations had predicted the thrust output within 5%. The engineers measured it carefully. The prototype generated approximately 1,240 pounds of static thrust, while consuming 90 gallons of fuel per hour. For comparison, contemporary piston engines produced thrust through propellers, making direct comparison difficult. But the jet engine was delivering power at a fraction of the weight and mechanical complexity. Word of the successful test reached the Air Ministry. Their response was a modest research contract. $5,000 to continue development. Not enough to build a flight-worthy engine. Not enough to hire a proper engineering team. Just enough to keep the project alive on life support, while officials debated whether jet propulsion was a worthwhile gamble. Whittle took the money and kept working. Europe was arming for war, and he'd just proven that aircraft could fly without propellers. Whether Britain would actually build jet fighters before the shooting started was a different question entirely. By 1939, Whittle had a functioning engine and a bureaucratic nightmare. The Air Ministry acknowledged his work, but moved with peacetime caution, forming committees to study the jet propulsion question, while Hitler's Luftwaffe prepared to dominate European skies with conventional aircraft. Power jets received enough funding to continue research, but not enough to build production engines. Whittle spent 3 years improving his design while watching the calendar run out. The second-generation engine, designated W1, ran successfully in December 1940. It produced 850 pounds of thrust, weighed just 623 pounds, and demonstrated remarkable reliability compared to the explosive prototype of 1937. Whittle had solved the combustion instability, upgraded the compressor efficiency, and developed better turbine blade metallurgy to handle the scorching exhaust temperatures. On paper, Britain now possessed the world's first practical jet engine. Integrating it into an actual aircraft took another year. The Gloucester Aircraft Company designed the E-2D-839, a stubby experimental plane built specifically around Whittle's engine. It looked nothing like conventional fighters. No propeller, an air intake in the nose, exhaust blast from the tail. The design was so radical that Gloucester built it in secret, telling curious observers they were working on a new type of turbine research equipment. On May 15, 1941, test pilot Jerry Sayer climbed into the E-2839 at RAF Cranwell, the same airfield where Whittle had been a cadet, dreaming about jet engines 13 years earlier. The takeoff run lasted 17 seconds before the aircraft lifted smoothly into the evening sky. It climbed faster than any British fighter then in service. Sayer later reported the flight felt eerily smooth, without the vibration that plagued propeller aircraft. The jet age had begun. But while Britain moved cautiously, Germany had been running a parallel program. Hans von Ohain, a German physicist, had independently invented a jet engine without any knowledge of Whittle's work. Ernst Heinkel, an aircraft manufacturer willing to take risks the British establishment wouldn't, funded von Ohain's research. The Heinkel He-178 had already flown in August 1939, nearly 2 years before Whittle's engine took to the air. The Germans moved faster. By 1941, Messerschmitt was developing the Me-262, a twin-jet fighter designed for combat. German engineers had access to better materials, larger budgets, and leadership that understood jet aircraft could change the war's outcome. Whittle's technical lead had evaporated while British committees debated production priorities. The Air Ministry's response to the E-2839's success was telling. They ordered fewer than a dozen development aircraft. Jet propulsion was proven, yes, but production factories were committed to building Spitfires and Hurricanes, proven fighters desperately needed for the Battle of Britain's aftermath. Retooling for jet production seemed risky when conventional aircraft were winning fights. Whittle watched the Germans pull ahead. Intelligence reports filtered back, showing Luftwaffe jet prototypes flying faster than anything the RAF could field. The technology he'd invented in 1928 and proven in 1937 was about to enter combat under swastikas, while Britain deliberated. Then the Americans entered the war, and everything changed. General Henry Hap Arnold, commanding the U.S. Army Air Forces, visited Britain in April 1941 and witnessed the E-28-39's flight tests. Arnold immediately understood what he was seeing, a revolutionary technology that could make every propeller-driven aircraft obsolete. He wanted it for America, and he wanted it immediately. The British government, desperate for American industrial might and facing German jets, agreed to share Whittle's complete technical specifications under wartime alliance terms. Arnold sent the drawings to General Electric with orders to build an American jet engine as fast as physically possible. The crate arrived at General Electric's plant in Lynn, Massachusetts on October 1, 1941. Inside, one complete Whittle W1X jet engine, stripped from a British test aircraft and shipped across the Atlantic. Accompanying it were complete technical drawings, metallurgy specifications, and a team of British engineers sworn to secrecy. General Electric had exactly 6 months to reverse engineer, redesign, and manufacture an American version. GE assigned the project to their supercharger division, the engineers who understood high-speed rotating machinery and compressed airflow. They unpacked Whittle's engine and immediately confronted a problem. British manufacturing techniques didn't translate directly to American factories. Imperial measurements had to convert to American standard. British specialty alloys required finding domestic equivalents. Every combustion chamber, every turbine blade, every fuel injector needed adaptation. The GE team worked around the clock through late 1941 and early 1942. They designated their version the IA, keeping Whittle's centrifugal compressor design, but upgrading components where American metallurgy offered advantages. The combustion chambers received improved fuel atomizers. The turbine blades used nickel-chromium alloys that could withstand higher temperatures. By March 1942, GE had their first IA engine running on test stands, producing more than 250 pounds of thrust. Meanwhile, Bell Aircraft received orders to design America's first jet fighter around GE's engine. The contract specified extreme urgency. The XP-59A Aerocomet had to fly before 1942 ended. Bell's engineers worked from rough performance estimates since the IA engine was still under development. When they finalized the airframe design, they built a twin-engine aircraft, mounting one GE jet under each wing, figuring redundancy was wise for such unproven technology. Security around the program was obsessive. The Army Air Forces classified the entire project above top secret. Bell constructed the XP-59A at a remote facility, trucked components separately to avoid attention, and spread disinformation that they were building a new propeller fighter. When they needed to test taxi the aircraft, they bolted a fake propeller to the nose to fool observers. On September 12, 1942, the XP-59A and its support team traveled by guarded convoy to Muroc Dry Lake in California, a remote desert location far from curious eyes. Test pilot Robert Stanley performed taxi tests, getting a feel for the aircraft's handling at high speed. The jet engines ran smoothly, their distinctive whine echoing across the empty lake bed. October 1, 1942. Exactly 1 year after Whittle's engine had arrived in Massachusetts, Stanley advanced the throttles to full power. The twin jets pushed the XP-59A down the dry lake bed, accelerating faster than any American aircraft had moved without a propeller. At 100 miles per hour, Stanley eased back on the stick. The aircraft lifted off smoothly and climbed into the California sky. The flight lasted about 15 minutes. Stanley kept it conservative. Basic handling checks, gentle turns, cautious climb rates. But the XP-59A flew. 2 American-built jet engines derived from Whittle's British design were propelling an American fighter through the air without a single propeller blade. The technology transfer had worked. General Arnold received the news in Washington and immediately ordered production expansion. GE scaled up engine manufacturing. Bell refined the XP-59A design. Other manufacturers received contracts to develop improved jet fighters. Lockheed began work on what would become the P-80 Shooting Star, America's first operational jet fighter. The Germans still held the technical lead. Their Me-262 jets were faster, more refined, and entering Luftwaffe service while American jets remained experimental. But American industrial capacity was awakening to jet propulsion, and once that machinery started moving, it would be unstoppable. Whittle's rejected design, ignored by British bureaucrats for a decade, was about to mass-produce American air superiority. The Bell XP-59A never saw combat. Flight testing through 1943 revealed the aircraft was underpowered, sluggish compared to the latest propeller fighters, and unsuitable for frontline service. The Army Air Forces ordered 66 Aerocomets total, using them exclusively for pilot training and jet propulsion research. As America's first jet, the XP-59A served its purpose, proving the technology and teaching engineers what worked and what didn't. Lockheed learned from Bell's limitations. Their P-80 Shooting Star, first flown in January 1944, represented a massive leap forward. It mounted a single, more powerful engine, the General Electric I-40, producing 4,000 pounds of thrust compared to the IA's 1,250. The P-80 could reach 558 miles per hour, making it faster than any propeller fighter in American service. The design was cleaner, the airframe lighter, the performance finally good enough to challenge enemy aircraft. But the war in Europe ended before P-80s could deploy in significant numbers. Germany's Me-262 jets had entered combat in 1944, shooting down Allied bombers and demonstrating jet superiority in heartbreaking fashion. Fortunately for the Allies, Hitler's interference with production priorities and Germany's collapsing industrial base limited Me-262 deployment to around 1,400 aircraft. Many never flew due to fuel shortages and pilot scarcity. The jet revolution that could have changed the war's outcome arrived too late to save Germany. The Pacific theaters saw similar timing. Japan had developed their own jet fighters, the Nakajima Kikka and others, but produced only prototypes before surrendering. P-80s reached Italy in early 1945 but never encountered enemy aircraft. The war ended with jets proven but unused in the decisive battles. The real transformation came afterward. With peace declared and propeller technology clearly obsolete, every air force worldwide pivoted to jet development. The USSR had captured German engineers and Me-262 prototypes, immediately starting their own programs. Britain continued refining Whittle's designs into the Gloucester Meteor, which entered RAF service. America poured resources into next-generation fighters. General Electric and Pratt & Whitney became jet engine powerhouses, but both owed their foundation to Whittle's core principles. Compress air, add fuel, ignite, extract some energy to power the compressor, blast the rest out as thrust. The centrifugal compressor eventually gave way to more efficient axial flow designs, but the thermodynamic cycle remained Whittle's invention. By 1947, American jet fighters were breaking sound barriers. The Bell X-1, powered by a rocket rather than a jet, but validated by the same high-speed research program, exceeded Mach 1 in October. The North American F-86 Sabre, using an axial flow jet engine derived from wartime research, entered production as America's premier fighter. When war erupted in Korea in 1950, F-86 faced Soviet-built MiG-15s in the first all-jet air battles in history. The jets performed exactly as Whittle had predicted back in 1928. They excelled at high altitudes where thin air choked piston engines. They sustained high speeds without propeller efficiency losses. They delivered thrust through pure reaction force, simple and reliable once the engineering challenges were solved. Korean War pilots confirmed what the mathematics had always shown. Jet propulsion was superior in every measurable way. Commercial aviation followed the military's lead. De Havilland launched the Comet jet airliner in 1952. Boeing's 707 entered service in 1958, crossing the Atlantic in 6 hours instead of 12 and making intercontinental travel accessible to millions. The jet age shrank the world, exactly as Whittle had imagined 3 decades earlier when everyone told him it was impossible. America dominated this new era, flying jets designed from British technology that British leadership had nearly abandoned. The numbers told the story of transformation. In 1945, commercial aviation carried passengers in propeller aircraft cruising at 180 miles per hour. By 1960, Boeing 707s crossed continents at 550 miles per hour, flying at 35,000 feet, where propeller planes couldn't operate. Pan Am launched transatlantic jet service in 1958. Within 5 years, propeller airliners were obsolete. The technology Whittle sketched in 1928 had remade global transportation in a single generation. Military aviation underwent even more radical change. The Korean War proved jets dominated air combat, but the aircraft were still recognizably related to World War II designs: swept wings, simple afterburners, guns as primary weapons. By the late 1950s, fighters like the F-104 Starfighter could exceed Mach 2, climb to 50,000 feet in minutes, and carried guided missiles instead of machine guns. The performance envelope had exploded. Every advance traced back to Whittle's core innovation. The axial flow compressor that replaced his centrifugal design worked on identical thermodynamic principles: compress, burn, expand, extract, thrust. Afterburners injected fuel into the exhaust stream for extra thrust, but they relied on Whittle's combustion chamber fundamentals. Turbofan engines added a ducted fan for efficiency, yet the gas generator core remained a Whittle-type turbojet. American manufacturers rode this wave to global dominance. Pratt & Whitney's J-57 engine powered the F-100 Super Sabre, the B-52 bomber, the 707 airliner, and dozens of other aircraft. General Electric's J-79 propelled the F-104 and F-4 Phantom. These engines generated billions in revenue, equipped Allied air forces worldwide, and established American technological superiority that would last decades. Britain, despite inventing the jet engine, struggled to capitalize commercially. Whittle's original company, Power Jets, was nationalized in 1944. The government seized it, compensating Whittle with a $100,000, but eliminating any possibility of building a private jet engine industry around his patents. Rolls-Royce and Bristol developed excellent engines, but they competed in a market increasingly dominated by American scale and marketing. The irony was brutal. Whittle had invented jet propulsion while British bureaucrats dismissed it. He'd proven it worked while officials delayed production. He'd shared the technology with America under wartime necessity. And now American companies were selling jet engines worldwide, while British aviation declined into secondary status. Whittle himself received recognition that felt hollow. He was promoted to Air Commodore in 1943, knighted in 1948. Awarded $100,000 by the Royal Commission on Awards to Inventors, a sum that sounds generous until compared to the billions his invention generated for others. He retired from the RAF in 1948 at age 41, his health damaged by years of overwork and stress. The stress was real. Whittle had driven himself mercilessly through the development years, working 20-hour days, smoking heavily, sleeping poorly. The combination of technical pressure, bureaucratic frustration, and wartime urgency had ground him down. He'd achieved his engineering goal, but paid a severe personal price. Post-retirement, Whittle worked as a technical consultant, wrote his memoir, and watched the jet age unfold without him at its center. He saw 707s shrink the Atlantic, saw supersonic fighters patrol the skies, saw his principles embedded in every turbine spinning worldwide. The validation was complete, but it came wrapped in bitterness. In 1976, at age 69, Whittle emigrated to America, the country that had actually built the jet age he'd invented. He took a position at the U.S. Naval Academy, teaching engineering and advising on propulsion research. Britain had given him a title. America gave him a second career and recognition from engineers who understood exactly what he'd achieved. Frank Whittle died on August 9, 1996, in Columbia, Maryland, at age 89. By then, jet engines powered virtually every aircraft carrying passengers or military missions worldwide. Over 100,000 commercial flights departed daily, each one using turbofan engines descended directly from his 1930 patent. The global aviation industry generated $300 billion annually. Whittle's invention had become so fundamental to modern life that most people never thought about it. The recognition that eluded him during his productive years eventually arrived, though late. Britain awarded him the Order of Merit in 1986, one of the nation's highest honors, limited to 24 living recipients. The U.S. awarded him the Charles Stark Draper Prize in 1991, engineering's equivalent of the Nobel Prize, with $500,000 attached. These accolades came when Whittle was in his 80s, decades after the struggles that had defined his life. History's judgment proved more generous than his contemporaries had been. Aviation historians universally credit Whittle as the father of jet propulsion, noting that while Hans von Ohain developed Germany's jet independently, Whittle filed patents years earlier and overcame far greater institutional resistance. Ohain himself acknowledged Whittle's priority, and the two men met several times in later years, forming a mutual respect between engineers who'd solved the same problem from different directions. The impact measurements are staggering. Before jets, crossing the Atlantic required days by ship or 12 hours in a propeller airliner, affordable only to the wealthy. By the 1970s, millions of middle-class passengers flew internationally each year, paying inflation-adjusted fares that had dropped by 60%. Jet engines made that possible. Global trade accelerated because cargo could move by air. Military power projection became viable because jets could deploy anywhere within hours. Commercial aviation alone employed 65 million people worldwide by 2019, generating $2.7 trillion in economic activity. The Boeing 747, introduced in 1970, could carry 400 passengers at 570 miles per hour for 7,000 miles. Performance impossible without turbofan engines, producing 50,000 pounds of thrust each. Every one of those engines operated on Whittle's 1930 patent principles. compress air centrifugally or axially, burn fuel in the compressed air, extract power via turbine, exhaust the rest as thrust. The military transformation was equally profound. The F-15 Eagle, entering service in 1976, could accelerate vertically, cruise at 50,000 feet, and sustain Mach 2.5, capabilities rendering World War II fighters as obsolete as biplanes. Modern air superiority rested entirely on jet propulsion. America's military reach, its ability to project power globally within hours, derived from Whittle's work in that Rugby workshop in 1937. Yet Whittle himself struggled with depression through much of his later life. He'd battled bureaucracy for decades, watched Germany beat Britain to operational jets, saw America dominate the industry his invention created, and received relatively modest financial compensation while others built fortunes. His first marriage collapsed under the stress. His health never fully recovered from the wartime years. The bitterness showed in his memoir, published in 1953. Whittle wrote frankly about the Air Ministry's short-sightedness, the funding struggles, the years wasted while officials debated and delayed. He didn't hide his frustration at watching inferior technology receive priority, while his proven engine languished. The book reads like a vindication document, a detailed case that he was right and they were wrong. He was right. The entire world now operated on principles he'd calculated in 1928, while his instructors called him impractical. Every jet aircraft proved his mathematics correct. Every commercial flight validated his rejected thesis. Every supersonic fighter demonstrated that the impossible fantasy was actually just engineering waiting to happen. The tragedy was that Whittle had to fight so hard to prove what should have been obvious. The lesson in Whittle's story isn't just about persistence or vindication. It's about the cost of institutional blindness. Between 1930 and 1936, while Whittle's patent gathered dust, Britain possessed exclusive rights to technology that would define the next century of aviation. The Air Ministry could have funded development for less than the cost of a single bomber squadron. They didn't, because the people making decisions couldn't imagine propeller aircraft becoming obsolete. That failure nearly cost Britain the war. When Me-262 jets appeared over Germany in 1944, shooting down Allied bombers at will, RAF pilots were still flying propeller fighters. The technology gap was entirely artificial. Britain had invented jet propulsion 14 years earlier. Bureaucratic caution and expert dismissal had handed Germany a potential war-winning advantage. Only Hitler's strategic incompetence and Germany's collapsing industry prevented jet fighters from changing the war's outcome. The pattern repeats throughout history. Revolutionary technologies emerge from individuals working outside established institutions, face rejection by experts invested in current paradigms, then transform the world after years of needless delay. Whittle's jet engine, the Wright brothers' aircraft, Claude Shannon's information theory. Innovations that seem obvious in retrospect faced dismissal when they appeared. What made Whittle's case particularly cruel was that he did everything right. He performed rigorous calculations. He filed patents. He built working prototypes. He demonstrated successful operation. At every stage, his work met or exceeded the standards that should have warranted support. The rejection wasn't because his engineering was flawed. It was because decision-makers couldn't envision a future different from the present. Consider the counterfactual. If Britain had funded Whittle properly in 1930, operational jet fighters could have entered RAF service by 1938. The Battle of Britain would have been one-sided. The strategic bombing campaign against Germany would have faced minimal opposition. The entire trajectory of World War II changes if one technology appears 5 years earlier than it did. Instead, Whittle spent the most productive decade of his engineering career scraping for funding, teaching classes to pay bills, and watching his revolutionary design languish because officials preferred incremental improvements to existing technology over fundamental breakthroughs. Britain eventually got jet fighters. after America turned Whittle's designs into mass production and changed the balance of power permanently. The financial irony compounds the tragedy. Whittle received $100,000 in total recognition from the British government. Pratt & Whitney and General Electric, using technology derived from his work, generated billions in revenue. Boeing built an empire on jet airliners using Whittle's principles. The engineers who refined and commercialized his invention became wealthy. Whittle died comfortably, but not rich, teaching at the Naval Academy because America appreciated his contribution more than Britain had. His legacy endures in every aircraft flying today. The turbofan engines powering modern airliners are evolved versions of Whittle's turbojet, more efficient, but operating on identical thermodynamic principles. The fighter jets protecting nations worldwide trace their lineage to his 1930 patent. Supersonic flight, global air travel, rapid military deployment, all rest on the foundation Whittle laid when he was 22 years old, and everyone told him it was impossible. Frank Whittle proved that one engineer with correct mathematics and stubborn determination could change the world despite institutional opposition. He also proved that doing so exacts a brutal personal cost, that vindication often arrives too late, and that bureaucracies would rather defend the present than build the future. Every time a jet engine spins up for takeoff, creating thrust through compressed air and controlled combustion, exactly as Whittle calculated in 1928, his story repeats: the impossible was always possible. Someone just had to survive long enough to prove it.